Hello guys, and welcome back to the PyTorch basics. In this video we're going to continue to learn about stacking and flattening operations. Since these two concepts need a lot of clarification, they need one whole video to explain them in detail. In past posts we learned about a tensor's shape and then about reshaping operations. A flatten operation is a specific type of reshaping operation whereby all of the axes are smooshed or squashed together. To flatten a tensor, we need to have at least two axes. This makes it so that we are starting with something that is not already flat. So if you want to flatten a tensor, you need to make sure that it has at least two axes to begin with, because if it is already flat, it cannot be flattened again. For example, the MNIST dataset contains 28 by 28 images. These two axes are of the height and width, which can be flattened out into a single axis of length 324, which is a product of 28 by 28, by using the flatten operation. In this example, we are flattening the entire tensor image, but what if we want to only flatten specific axes within the tensor? This is typically required when working with CNNs. So in this case, we're flattening the entire tensor. But what if we want to define a specific axis to flatten the tensor? So tensor inputs to a convolutional neural network typically have four axes: one for batch size, one for color channels, and one each for the height and width. So the input shape for a neural network using PyTorch, first you must define the batch size, or how many images you have in a batch. Second, you have to define the number of channels. For an RGB image, you might have 3 number of channels, and for a grayscale image, you might have 1 channel. Next is the height of the image, and the last is the width of the image. If you are working with other deep learning frameworks such as Keras, the order of the dimensions may not be the same as PyTorch. So moving on, in order to avoid any confusion, we will be proceeding with this type of input shape. Let's kick things off here by constructing a tensor to play around with that meets these specs. To start, let's create the following 3 tensors. So these are the 3 tensors we're going to be creating. Each of these has a shape of 4 by 4. So we have 3 rank 2 tensors because we have height and width. For our purposes here, we will consider these to be 3 4 by 4 images that we will use to create a batch that can be passed into a CNN. So you can consider this to be 3 images with a dimension of 4 by 4. So we can define the shape for our input by using the aforementioned input shape. Remember, batches are represented using a single tensor. So we will need to combine these 3 tensors into a single larger tensor that has 3 axes instead of 2. So since the three tensors are clearly not combined together, they're separate tensors, we need to combine them into one that contains three images and with a height and width of 4 by 4. So the shape might be 3, 4, and 4. In order to do that, we're going to introduce a new concept called stacking. Here we used that stack method to concatenate our sequence of three tensors along a new axis. So since our current axis only contains 2, which is the height and width, and we need to add an additional axis in order to concatenate our tensors, we need to define a third axis. So a stacking operation always concatenates tensors in a new axis. That's what you need to remember about stacking operation. It doesn't concatenate along the same dimension, but it creates a new one to concatenate the tensors. Since we have three tensors along a new axis, we have now the length of this axis should be 3. And indeed, we can see that in the shape that we have three tensors that have height and width of 4. So let's imagine these are the tensors, and we defined a new axis and we stack them on top of one another. So instead of having a dimension of 4 by 4 only for each one, which is a rank 2 tensor, now you have a 3, which indicates the number of images, and 4 by 4, which indicates the dimensions of one image. The axis with a length of 4 represents the batch size, so 3 represents the batch size, while the axis of length and 4 represents the height and width respectively. Previously, we have seen about concatenation, but what is the difference between stacking and concatenating? So concatenating joins a sequence of tensors along an existing axis. The PyTorch function for concatenation is cat. Stacking joins a sequence of tensors along a new axis. So that's the only difference between the two. Both of them can be used to stack tensors, but we have to make some modification on concatenation to perform the same operation as stacking, because concatenation only joins the tensors along the existing dimension or the existing axis, but stacking creates a new axis for the concatenation operation. Let's look at an example where we stack three tensors into one tensor using stack. So here we're going to create 4 one-dimensional tensors, and it has the number of elements is 4. I mean, we create 3 different tensors, and each of them are one-dimensional tensors with 4 elements. In the above code, the tensors x, y, and z are one-dimensional, each having 4 elements. Next, we will stack the tensors along dim is equal to 0 and dim is equal to 1 across the zeros axis and the first axis. So by using the stack operation, we add the 3 tensors together as a tuple. And first we're defining the dimension to be 0. Now when we print the stacked tensor, now the size or the shape is 3 by 4. Remember that it's just a one-dimensional tensor with 4 elements first, but stacking operation created a new axis, and since we are combining 3 tensors, the number of tensors defines the number of elements on the new axis, which is 3. And since we define the axis to be 0, it's stacking them across the row, which means on axis 0. Next, we're going to do the same thing, but we're going to change dim is equal to 1. Now we're stacking them in across axis 1 instead of 0. Now you can see it's stacking the one-dimensional tensors across the column. So the new dimension or the new axis will be added on the as a second element for the shape. Now you can see the 3 is defined on axis 1. Notice that the elements are transposed before being stacked as a column. So this tensor is a rank 2 tensor, but the previous tensors were rank 1 tensors. The resultant concatenating tensor is 2-dimensional. As the individual tensors are 1-dimensional, we can stack them with dimensions 0 and 1. So with dim is equal to 0, the resulting matrix will be a 3x4 matrix. And with dim is equal to 1, the resulting matrix will be a 4x3 matrix. We can derive the same results of the stack function using the cat function. Now we're going to use cat to create the same matrix instead of stack. We can apply the unsqueeze operation to each tensor before passing them to the cat function to get the same result. Let's look at the result with the tensors from the previous example. We're going to be using the same example. So, in order to create the matrix using the concatenation function, cat, first we need to unsqueeze each tensor. Unsqueezing, if you remember from the previous video, it's going to add a new dimension, a new axis, but it's going to be 1. So each of these are going to have a shape of 1x4 instead of just 4. Since we are unsqueezing across axis 0, remember that we must define the axis in which we want to unsqueeze. Then we're going to define dim is equal to 0 for the stacking operation. So the only difference between cat and stack to create a matrix with a new dimension is the unsqueezing operation on each tensor before passing them as an argument. Now you can see that across dim equal to 0, it's doing the same thing. We created a 3x4 matrix, just like the stacking operation. Therefore, torch.stack is the same as concatenation operation. The only difference is using the unsqueezing operation. Now we have added a different number of batch size to our original tensor. So at this point we have a rank 3 tensor that contains a batch of 3 4x4 images. So the shape is 3 times 4 times 4. All we need to do now to get this tensor into a form that a CNN expects is to add an axis for the color channels. We basically have an implicit single color channel for each of these image tensors. So in practice, these would be grayscale images. Since we are now considering the images to be grayscale, we're going to add an additional dimension for the number of channels to be 1, since grayscale images only have a single color channel. So we're going to transform the shape from 3 by 4 by 4 to 3 by 1 by 4 by 4, because the second axis with the 1 represents the number of channels. Now you can see here we're going to reshape the original tensor from a 3 by 4 by 4 to a 3 by 1 by 4 by 4, and this is going to create a new tensor with this shape. As you can see, the first bracket indicates the number of images, 1, 2, and 3. The second bracket indicates the number of channels. Since we have only one channel, we have one bracket inside each batch. And finally, we have the height and width dimension, the width and column, 4 by 4. CNN will expect to see an explicit color channel axis, so let's add one by reshaping this tensor. Then notice that we have specified an axis of length 1 right after the batch size axis. Then we follow the height and width axis length 4. Also notice that the additional axis of length 1 doesn't change the number of elements in the tensor. Since the original number of elements is the product of all of these numbers, adding the 1 doesn't change because the product still stays the same when we multiply by 1. The first axis has 3 elements. Each element of the first axis represents an image. Image 1, image 2, and image 3. For each image we have a single color channel on the channel axis, so we have a single channel. And each of these channels contain 4 arrays that contain 4 numbers or scalar components. Let's see this with code by indexing into this tensor. We have the first image, so when we index by using only one index, 0, we're going to get the first image. We have the first color channel in the first image, so when we want to get the first color channel within the first image, we use the second index 0. And when we have the first row of pixels in the first color channel of the first image, so the first image, the first color channel, and the first row, and when we have the first pixel value in the first row of the first color channel of the first image, we need 4 indexes, which means we selected the first row and then we just select the first element. Now let's see the flatten operation and how to flatten the whole image into just a single dimension. So remember, the whole batch is a single tensor that will be passed into a CNN. So we don't want to flatten the whole thing, we only want to flatten the image tensors within the batch tensor. So remember, when you pass images into a CNN and when you want to flatten them, you only need to flatten them across each image, and you don't want the case, because the flatten method will just completely squish everything into a single dimension. Let's flatten the whole thing first, just to see what it looks like. The image on the left shows 4 ways that can be used to flatten the whole batch. So if you want to flatten the whole thing, we can use the reshape operation first. We can specify 1 and then we can specify -1. As you remember, if we specify -1, it's going to calculate the shape by itself. Since we have an incoming 3 by 1 by 4 by 4, they're going to be multiplied and replaced here. Then we access the first element because the shape now is 1 by 384. And in order to remove the 1, then we select the first element if you use this kind of method. But if you just use -1, it's not going to have a shape of 1 by 384, but only 384. So here you don't need to use the indexing. Remember that we can use the view method, which can do the same thing as reshape. And instead of -1, you can use PyTorch's numl function, which calculates the number of elements in the tensor. This is the same as 384. And t.flatten is the built-in PyTorch function that will just flatten the whole thing. All of these perform the same thing, but I'm just putting them here so that you can see what's happening behind the scene and the different methods you can use to flatten the entire tensor. If you don't specify any arguments here, it's going to just squish everything into one-dimensional tensor, no matter the shape. What I want you to notice about this output is that we have flattened the entire batch, and this smashes all the images together into a single axis. Remember, the ones represent the pixels from the first image, the 2's represent the second image, and the 3's represent the third image. This flattened batch won't work well inside our CNN because we need individual predictions for each image within our batch tensor, and now we have a flattened mess. Because since we have squished everything into a single dimensional tensor, there is no difference between the first image, the second image, and the third image. And if you want to make predictions, since everything is smooshed together, we can no longer have the shape of the first, second, and third image. So what if we want to flatten the first image only, the second image and the third image separately, but not combining them together? We need to preserve one axis at least. The solution here is to flatten each image while still maintaining the batch axis. This means we want to preserve the first axis, which is the number of images in a batch, the batch size. So in the original shape we have 3 by 1 by 4 by 4. So we want to do the flattening across the channels and not the batch. This means we want to flatten only part of the tensor. We want to flatten the color channel axis with the height and width axis. So the axes need to be flattened into the channel height and width. Okay, let's run the following code. Now, instead of using the flatten operation with no arguments, we're going to pass an argument called startDim, and we're going to assign a value of 1. And when we use the dot shape attribute, we can see that the new shape will be, instead of 3 by 1 by 4 by 4, we're going to have 3 by 16. And when we print out the output, we can see that each image is still preserved and they're not combined together. Remember that this is the first image. It was a 4 by 4 image, but now it's just a 16 elements, one-dimensional. So startDim is equal to 1 means start from the first axis to perform the flattening operation. Skip the first axis, which is axis 0. Remember, if you don't provide any arguments here, the default will be 0, and then it will flatten everything. and it's not preserving the first axis. Notice in the call how we specified the start_dim parameter. This tells the flatten method which axis it should start the flatten operation. The 1 here is an index, so it's the second axis, which is the color channel axis. We skip over the batch axis, so to speak, leaving it intact. So the batch axis, the 3 images are still preserved. Checking the shape, we can see we have a rank 2 tensor with 3 single color channel images that have been flattened out into 16 pixels. Okay, what happens if we flatten an RGB image? If we flatten an RGB image, each color channel will be flattened first. Then the flattened channels will be lined up side by side on a single axis of the tensor. Let's look at an example in the code. And here we have torch.once with a shape of 1 by 2 by 2. Notice that we are using the concatenation operation instead of stacking. So if you want to combine these 2 by 2 RGB channels, so this is just a single 2 by 2 image with an RGB channel. If you want to use the stack operation, you don't need to specify the 1, because the unsqueezing operation is the one that adds a new axis for the concatenation, because it will combine them on the mentioned dimension or the existing axis. But if you want to concatenate them and stack them on a different axis, then you need to use stack, or if you use concatenate, you need to add the 1 so that it adds a new axis first and then it combines them across the new axis. Here we have once a 2 by 2 tensor with all elements being 1. Here we add a 1, and by broadcasting, which we will see in the next video, we're going to add 1 to each element. So this tensor will be a 2 by 2 tensor with all elements being 2, and this one will be 3. This gives us the desired tensor. We can verify this by checking the shape. So it's going to combine the 3 tensors, 2 by 2 tensors, along a new axis, and since we have 3 tensors, the new axis will have a shape of 3. We have 3 color channels with a height and width of 2. We can also inspect this tensor's data like so. So if we print out the whole tensor, now we have a 2 by 2 tensors, and each of them have, and this indicates the channels, and we have 3 channels RGB. Now we can see how this will look by flattening the image tensor. Now by using the flatten operation and defining start_dim is equal to 0, since this is the default, it's going to flatten everything into a one-dimensional array, no matter the previous shape. But if you want to preserve the channels, note that the start_dim parameter here tells the flatten method where to start flattening. In this case, we're flattening the whole image because we're starting from the channels, and it already had 3 channels, but those will not be preserved because the flatten operation starts from the number of channels. But if we change the start_dim to 1, it's going to start flattening from the second axis. So this means it's going to preserve the channel dimension, and it's going to flatten each image. So each of these were a 2 by 2, now they're just one-dimensional. That's all for stacking, concatenation, and flatten operation. Next, we're gonna implement them using PyTorch as a coding exercise. Okay, last time we stopped here for the coding exercise. So now we're gonna cover the stacking operation first. First, we need to create 3 4x4 tensors. And first, let's import Torch. Now, they are already defined. We mentioned that the stack operation concatenates our sequence of 3 tensors along a new axis. So these 4x4 tensors are going to be combined on a new axis, and since we have 3 tensors, the new shape will be a 3x4x4. Now it's already defined, and we can print T. Here we see that they have been stacked on a new axis, and we can also see the shape. Now you can see that the shape of the new tensor is a 3x4x4. Since we have 3 tensors along a new axis, we know that the length of this axis should be 3. And we can think of the additional axes as the batch number. So this 3 is just the batch size. Now we're going to add the number of channels in between, so we're going to reshape the original tensor from 3x4x4 to 3x1x4x4. And notice, since we're just only adding 1, since the product and the number of elements are preserved, the reshape operation is going to work. Now we can print the new one. Here notice originally we only have 3 brackets, and now we have 4 brackets, which means we have an additional 1 bracket for the channel. We can also check the shape. And now we can see that it's already changed to a 3x1x4x4 tensor. Now if we want to access the first batch or image, we can just use the zeros index from the 3 images, which is going to give us the first one, which is only the ones. And if we want to access the channel, the first channel, we can add an additional index 0, which is this bracket. Now we see we have the first channel. If we want to index the first row, then we can add an additional index 0. Now we accessed the first row, and if we want to access the first element from the first row, we can add an additional index 0. Now you can see that we have accessed the first element. Next, we're going to see the difference between stack and concatenation operation. Here we're going to define 3 new tensors, one-dimensional tensors. Notice the first one has 4 elements, the second one has 3 elements, and the third one has 6 elements. First, we're going to use concatenation operation and concatenate them along the axis 0. Since each of them are only one-dimensional, concatenation only works along an existing dimension, and since we have only one dimension, which is the one axis, it's going to concatenate them and combine them into a single one-dimensional tensor. Now we're going to output the tensor and see the shape. As I have mentioned, it combines them into a single tensor because it's combining them along an existing dimension. And the shape is just 13 elements. What if we want to combine them along a new dimension? We can use the stack operation, and we pass x, y, z, the 3 tensors we want to combine, and we define them as equal to 0. This is going to add an additional axis, and it's going to have a rank of 2 instead of just 1 rank, and it's going to combine them across the first axis, which means it's going to stack them across the row. Here you can see that stacking operation doesn't work if they're not equal size. So since they're not equal size, this is not going to work. Now let's try this again. Now you see that there are no errors. Now let's see the output after the stacking operation along dimension 0. Now you see that it has combined them across the row, and the new size will be 3 by 4. 3 indicates the number of tensors which are used to create the new tensor, and each of them have 4 elements. Next, let's stack them across the column instead of the row. We can do so by using dim is equal to 1. Then we can see the output. Now instead of being combined across the row, they're being combined across the column. So this is the first tensor, the second, and the third. Instead of being a 3 by 4 tensor, now it's going to be a 4 by 3 because the 4 elements are in the columns. If we want to stack them using concatenation instead of stacking, the only thing we need to do is just unsqueeze them and add a new axis on each tensor. So instead of being just 4, it's going to be 1 by 4 for each of them. And once we create that new axis, concatenation is going to work across the rows. Now when we see the output, it's going to be basically the same as the stacking operation. That's all for this video, and in the next video we're going to start to discuss about element-wise operations.
Audio Jungle.